This is our video on something called specific latent heat of fusion and specific latent heat of vaporization. And the idea is this: what actually happens when water boils? So imagine you've got some water on a Bunsen burner. What's going on? Well, the bubbles of water vapor form inside the water. So this tends to happen off the bottom, the hottest surface. What we're saying is liquid water turns into gaseous water or steam. But you might have noticed when you do this in year 7, the temperature doesn't rise. You can sit and boil a beaker of water all day and the temperature will not rise above 100 degrees once it's boiling. So the heating that you are doing is doing some kind of work on the water molecules, but what it's not doing is raising their temperature, raising the temperature of it. What's happened is that the work that's being done, the energy is being used to break the bonds and evaporate the water liquid into a gas, into gas or steam. So it's breaking the bonds and evaporating into vapor bubbles. So we've got this idea that from a liquid to a gas, the heat energy transferred in doesn't raise the temperature, but instead breaks the bonds and separates the molecules. So when bonds are being broken, what happens to the energy? That's our idea here. And when a gas is cooled, do we get this energy back somehow? Because if we're putting energy in, where does it go? And then how do we get that energy back when we're doing the reverse and not heating something if we're cooling something? Okay, and this is the idea of latent heat. Now, the word latent means hidden. So the answer to the question, where does the energy go? Well, it's hidden in that you can't see it, and it actually becomes part of a sort of a potential energy of the bonds of the material. And we've got two ways of describing latent heat. We've got latent heat of vaporization, which is the energy needed to vaporize a liquid to a gas or turn a liquid into a gas. And this energy will be released when the gas condenses from a gas back to a liquid. Then we've got something called latent heat of fusion, and this isn't to do with nuclear fusion, so don't get confused. This is latent heat of fusion, and this is the energy required to melt a solid into a liquid. So it's to turn a solid into a liquid. And again, this energy that's put in, the hidden energy that you put in that you don't know quite sure where it's gone in as potential energy, and then the energy will be released when the liquid solidifies. So when you turn something from a liquid to a solid, energy will be released. Okay, now you can see the evidence of this. You may have done this in the lab. If you set up a cooling curve, maybe stearic acid, and you effectively heat it up, and then it converts or it transforms from a liquid to a solid. And as it does, if you heat it up to about 90 degrees, here it's a liquid. And if you wait for a certain amount of time, it cools and cools and cools. And then when it gets to about 69 degrees, you will notice that the temperature stays pretty much the same. And what's happening here is that all of the energy is coming out. So all the energy that went in to break the bonds, that's stored as potential energy, all that energy is coming out of the bonds. So you don't get a temperature drop. The temperature stays constant. And then once it's all melted, so once all of the liquid once it's solidified, once all of the liquid has turned into a solid, so at the melting point, then we get the temperature drop of the solid all the way down, and this will eventually end up at room temperature. So you can see the evidence of this on a cooling curve, but what's a little bit easier to understand is if you imagine a graph of temperature against heat added, and this is quite a nice diagram here. So we've got all the different states. So we've got solid particles there, we've got liquid and solid, so we've got the particles in between a liquid and a solid melting, then we've got a liquid, then we've got between a gas and a liquid, and then we've got a gas. So you can see the particle transformations that are taking place at the top. Here's our formula, which is Q, which is ml, and Q is again the energy required or the energy needed, and this is the energy needed is the mass times the value of L, and we've got two possible values of L. We've got the specific latent heat of fusion for a substance, which is the energy needed to change 1 kilogram from a solid to a liquid, and I'm going to call that LF. And then you've also got the specific latent heat of vaporization for a substance, which is the energy needed to change 1 kilogram from a liquid to a gas. Let's call that LV. So the L in this formula can either be LF or LV. So let's consider the graph again. We've got bits that are a straight line, then we've got an increasing gradient, then we've got a flat bit, then an increasing gradient, then a flat bit. So here what we are saying, we are adding heat to our liquid solid mix, and the temperature is not going up. So this is where the latent heat is. The energy that we're adding at the flat bit is going into the potential energy of the bond, so we don't get a temperature increase. Once we've broken the bonds between the solid and the liquid, then we get a temperature increase as we add heat, and then we get our next latent heat. So this is the latent heat of vaporization, and here the energy that we put in is going in to break the bonds between the liquid, the particles in the liquid, and convert them to gas. Okay, all right, so this is why this graph looks like it does. And what we can do, we can label this graph up, and we can say in the straight bit all the energy is being converted to break the bonds. So we're saying this would be Q equals MLF, latent heat of fusion, and this is Q equals MLV, latent heat of vaporization. All right, and the energy is stored, as I've been saying, as a kind of a potential energy. Now, if we went back the other way, and if we allowed this to cool, this potential energy is released when the substance cools, and the bonds, either between the gas and the liquid, or the liquid and the solid, the bonds reform. So you'll get energy out. All right. Now the slopey bits. This is where what's going on here is this is normal specific heat capacity. So you've got the energy added is equal to the mass times the specific heat capacity times the change in temperature. So here we're heating the solid, and the amount of energy we put in depends on the mass and the change in temperature that it goes through. The flat bit, this Q equals MC delta T, does not apply. All right, so it's just a matter of getting your head around what we mean by specific heat capacity, specific latent heat, and how you can graphically show these on this temperature versus energy added graph.